Now we are going to see how to prove a function one-to-one and onto. Before proving a function is one-to-one or onto, you have to understand the definitions of one-to-one function. See, no element in the codomain B has more than one pre-images. For example, two elements in x1 and x2 have the same image, then it is not at all a one-to-one function. It is called a many-to-one function. And the definition of onto is all the elements in the codomain must have pre-image, at least one pre-image. Maybe it may have more than one pre-image, that doesn't matter. But all the elements in the codomain must have pre-images. This is how we can prove the function is one-to-one. If you assume f of x1 equal to f of x2 and if you get x1 equal to x2, then the function is one-to-one. In some cases, x1 can never be equal to x2. For example, x1 is prime number, x2 is an odd number, a composite number, x1 is a even number, x2 is an odd number. In those cases, x2 is positive, x1 is negative. In those cases, if you assume f of x1 equal to f of x2, you end up with a contradiction, then you can say f of x1 is not at all equal to f of x2 whenever x1 is not equal to x2. Thus, for all the values, two different values of x1 and x2, you'll have two different images. Therefore, it is one-to-one function. This is how we can easily prove a function being one-to-one. Let us see an example. F is a function from integers to integers, f of x equal to x square. If you assume f of x1 equal to f of x2, you end up getting x1 square equal to x2 square. That means if you bring everything to the same side, you'll have x1 minus x2 into x1 plus x2 equal to 0. So it could either be x1 minus x2 equal to 0 or x1 plus x2 equal to 0. But if x1 equal to minus x2, is there any possibility among the integers? Yes. If x1 is 7 and x2 is minus 7, then they're two different values, but you end up getting the same images. Let's see. Not for all x1 and x2, f of x equal to f of x2 gives x1 equal to x2. We give a contradiction to prove it, a counter to prove it. Let f of minus 3 and f of plus 3, both are equal to 9, but 3 and minus 3 are not equal. Thus, f is not one-to-one, it is many-to-one. Now, we shall see how to prove the function is onto. Let f is a function from a to b. Make sure the codomain equal to range. This is for R confirmation. Then write f of x equal to y. Try to write x in terms of y. I'm writing x equal to g of y. That doesn't mean that some other function. You're just writing x in terms of y. Now substitute this x of x equal to g of y, that x in terms of y in f of x. You definitely end up getting f of x equal to y. Then you can conclude for every y belongs to the codomain B, there exists an x belongs to the domain A. Thus f is onto function. In case the codomain is not equal to range, you find some value which is not in the range but in the codomain. If you make that is equal to f of x is equal to that one of the value which not in the range but in the codomain. For example, codomain is natural number, range is 5, 6, 7, 8 something. You just let f of x equal to 3, which is there in codomain but not in range. Then you get a contradiction that the pre-image does not even present in the domain. Therefore, this is not an onto function. For example, if you take f of x equal to y, x square equal to y for the same function, x is equal to root y, then values of y will be like 1, 0, 1, 4, 9, whichever is giving a perfect square root. So we'll find some value in the codomain, not in the range. A range is some set of values, some I wrote w here, it's not whole numbers. Range, I'm writing range as the w. So if you find a non-perfect square which lie in the codomain or a negative number which lie in the codomain, you cannot find pre-images for that thing. For example, if you assume f of x equal to 3, then x square equal to 3, x is equal to root 3, which is not an integer. So we don't have pre-image for 3 in the domain. Same way, if f of x is minus 4, x square equal to minus 4, then x is an imaginary value which is not an integer. So we can conclude f is not onto. Here is one more example with how we can use completion of square. Here we write f of x, the function is f from natural number to real number, but they modify the question. F is a function from n to s, where s is the range. So whatever the suitable values of the natural number for each and every x, you will get whatever the value that is to be taken as s. Well, f of x equal to 4x square plus 12x plus 15. I can write 4x square as 2x the whole square plus 2 into 2x into 3 plus 3 square plus 6, writing 15 as 9 plus 6, 9 as 3 square. Then it will be like 2x plus 3 the whole square plus 6. Now f of x1 equal to f of x2, similar procedure. Finally we get like 2x1 plus 2x2 plus 6. Obviously when I take 2 common, it will be like x1 plus x2 plus 3 in the bracket. That can never be equal to 0 because sum of two natural numbers is a natural number plus 3 is another natural number which is not at all equal to 0. Therefore x1 minus x2 equal to 0, thus x1 equal to x2. So the function is 1 to 1. It is given in the given range. So let us assume that range be S. Find f of x. F of x is being written in terms of x. Make that is equal to y. So 2x plus 3 the whole square plus 6 equal to y. Then 2x plus 3 equal to y minus 6. Since 2x plus 3 is a positive number, because x is a natural number, but 2x plus 3 is also a positive number, then 2x is equal to 2x plus 3 equal to plus root of y minus 6. It could be either plus or minus, because we know one thing, a square equal to b square, a equal to plus or minus b. But here 2x plus 3 the whole square equal to y minus 6, but 2x plus 3 equals plus root of y minus, because 2x plus 3 is positive. So 2x equals minus 3 plus root of y minus 6, x is equal to minus 3 plus root of y minus 6 by 2. Now we are substituting this x value in that f of x. Obviously you are going to get y because it came from that f of x itself. So this is a way you need to prove that function is onto. Okay, finally we can conclude one statement that therefore for every y belongs to the set S, the codomain S, there exists an x belongs to the domain natural number. Thus f is onto. Since f is both 1 to 1 and onto, it is invertible also.